Today's solubility lab, easy objective. We're going to find the solubility of KCl and of KNO3 in water at different temperatures. So we're going to be able to basically create a solubility curve. At different temperatures, what is the maximum amount of solute that can be dissolved in the solution based off of 100 grams? That's what we're trying to do. So the idea is that in our mind and the way the graph works, the temperature changes. We change the temperature and see what is the solubility. It turns out in practical ways, that's not actually so reasonable to do. So in practical ways, what we're really going to be doing is we're going to change the we're going to change the mixture and pick a solubility. And then we're going to change the temperature until it is saturated. And then we have our point. So we're going to be changing the temperature as opposed to changing the solubility. And it's a little bit of a different kind of task. But we end up getting the information the same in a way that's experimentally much easier to do. Yep. Come on. All right. So again, we're going to rehash some skills, weighing, burettes, filters. Really, you've already done all that, but just we'll be using those today. Learning how to make a saturated solution. So how do we get it to the point where it's saturated, at which we're going to call it solubility? How to graph data. And this is going to be a little bit tricky to get our graphs the way we want them to. Scaling, lots and lots of proportional scaling. Our standard is based off of having 100 grams of water, but reality is we often don't use 100 grams of water. We use less or more water, and I need to be able to scale, okay, what would the amount of solute be if it was 100 grams of water? And we're going to be scaling back and forth and back and forth. It's simple proportions, but you just have to be very clear in your mind of which is which. And understanding how to use a solubility curve to find the mass of solid in a mixture. Things I expect you to already know from 123 lab is how to weigh things out properly and how to condition a burette and use it to deliver a certain amount of volume. So I'm going to show the next two slides really quick. You can pause them if this is not familiar and go over it. If it is familiar, you're all set. Okay, so a solution is a fancy name for a homogeneous mixture. So remember, mixtures are more than one component. Homogeneous mixtures are ones that are so evenly distributed between the components that you can't tell that there's more than one component. It looks like one component. Realistically, on a particulate level, what that means is in order for that to be happening is we have two components. The stuff we have more of, we're going to call the stuff that there is the most of, the component that's the majority of the solution, is going to be called the solvent. It's often water. It doesn't have to be water, but it goes off of quantity. The stuff that there is the most quantity of is the solvent. And then the other things that I have less of, there may be one, there may be many, are solutes. The solute must be surrounded by solvent so that it is homogeneous, so that it's all distributed evenly. And that happens when water, or whatever solvent it is, we call it solvates. It surrounds the individual solute particles. And in the case of ionic compounds, we know that if they dissolve, meaning if water can surround individual pieces of it, they dissociate. So for an ionic compound, it'll be the two ions that compose the compound are now dissociated, and each is surrounded by the solvent molecules. That's what a solution is. So again, be careful about the vocabulary. Make sure you understand what we mean by solute and solvent. And when I say the word solution, it's the entire thing. So when we talk about solubility, now we are talking about a specific kind of solution, a homogeneous yet saturated solution. So when we talk about this is the how much solute can dissolve in a given solvent. That should be in a given solvent. Sorry, just caught that. So it's the ratio of the maximum amount of solute to solvent, or maximum amount of solute to the whole solution. So when a mixture has the maximum amount of solute that it can be dissolved, and yet it is still homogeneous, we call it a saturated solution. I couldn't call it a solution if it's not homogeneous. And there's a good way to really define this using equilibrium reactions and equilibrium terminology, which you're getting to in class about now, but we'll leave that for the class. So we refer to this thing called standard solubility, and it is defined as the mass of dissolved solute in 100 grams of solvent, but it has to be for a saturated solution. So it's implied when I say the word solubility. I could also measure the concentration of a solution in the same use, but it's not a solubility unless it's saturated. And it is different from our molarity and many of our other ones. In many of our other, if we do mass percent or we do molarity, they are a quantity of solute per the whole solution. So moles of solute per liter of solution for molarity, or grams of solute per grams of solution, which is the whole thing. So this one's a little bit different because I'm going to measure the two parts and I'm ratioing them. I could also measure solubility in mass percent. Again, mass percent is a normal way we describe mixtures. If it is saturated and homogeneous, then it could be the solubility in mass percent units. So it's the mass of dissolved solute divided by the mass of solution. So I would add the mass of the solutes and the solvent together and put that on the bottom. So the denominator changes, so the number changes, but it's still a proportion of how do I, what is the solution made up of? And again, we only say it's solubility if it is at fully saturated, it can't dissolve anymore, and yet it's still homogeneous. Okay, let's talk about the difference between solubility and mixture ratios. Just being clear, so a mixture ratio is just, hey, here's what's in a mixture. But mixtures could be homogeneous, and they could be heterogeneous, and they can be saturated, and they can be unsaturated. So let's go through these details. So solubility is measured by, well, let's talk about on the right. The mixed ratio of the mixtures is the amount of solute to the amount of solvent. I can use that ratio to describe any mixture. It might be unsaturated. It's homogeneous, but it doesn't have as much solute as it could. It could dissolve more solute if I had more. The mixture ratio is less than the solubility for that temperature, would describe an unsaturated solution. I could have saturated and homogeneous. There's no solid, everything's all dissolved, but it's at the maximum that can dissolve. That would be where the mixture ratio is equal to the solubility for that temperature. And the third possibility would be that it's saturated with solid, so it's maximum amount dissolved, but there's extra solute that is now in solid form because it can't dissolve, sitting at the bottom usually because it's heavier, sitting at the bottom of the solution. So it would be a heterogeneous because I have some part that looks like a liquid and some part that is solid. And that would be the mixture ratio would be greater than the solubility for that temperature. Also, if I wanted to know what proportion of mass was solid, I could use that by subtracting off the additional mass from the solubility for that ratio. And so I could figure out how much is dissolved. The remaining amount of the solute would be in solid form. Okay, on the left side again, how do I know that it's at saturation and it's a solubility? I could slowly heat a mixture that isn't fully dissolved, measuring exactly the temperature at which it all dissolves. So I could take with salad on the bottom, and I'm stirring it the whole time, and I heat it up, and when the last bit of solid dissolves, I'm like, oh, I'm at saturation. And I wouldn't want to continue heating because I could continue heating and it would be unsaturated. Or I could take an unsaturated solution. So it's all dissolved, and then I slowly cool it. And when I hit the point where I see the first bit of solid forming, the first crystals, that temperature would be the saturation point, and that would be solubility. So we're trying to find this mixture where everything is dissolved, and yet it's just at the point where any more solute added is going to be solid. And so once we have that, we can create this curve. Their curves exist already, and we can use those curves. Let's take a look at that. All right. Again, when we talk about scaling solubilities, we will do this a lot. Our standard solubility is ratio to 100 grams of water. And so I have to have almost like in a virtual world where here's my real solution. If I scaled it up, if I have less than 100 grams of water, I'm going to proportion it out and scale it up. What would be the solute mass if it was 100, if I had more of it? Or I could have much more than 100 grams of water, and I want to scale it down to, well, what would it be if I had 100? So it's almost like we have a left side, which is the actual mixture ratios, and the right side, which is these are what it would be as a ratio if I had 100 grams of water. It's just a proportion. So on the left, I see there's a mixture that has 3.8 grams of solute and 18.35 grams of water, and I want to scale it up to, but what would be the mass of solute if there was 100 grams of water, if I had more water, but it was the same concentration, same ratio of mixture. So I just simply solve for this, right? If I multiply both sides by 100, I isolate x. X is 3.8 times 100 divided by 18.35. So if I have a saturated solution and I know the mixtures, because I measured them in lab, I can convert it to a standard solubility. Or if I look up a standard solubility on a curve and I want to know, yes, but I don't want to use 100 grams of water, I want to use a different quantity. How much solute do I need? I can scale it to a mixture ratio of a different amount of water. In this case, I know that, let's say I looked up on a graph that saturation at a certain temperature is 60 grams of solute per 100 grams of water, but I'm only going to have 18.35 grams of water. I want to know how much it should be for that. So I would simply, it's the same idea. I'm going to multiply both sides by 18.35, and I solve for x. So two ways, and we're going to go back and forth. And again, I think you should, in your mind, mentally think about, I have my standard solution, which has to be 100 grams of water, and then I have my lab solution, which might be more or less than 100 grams of water. And you just scale back and forth. Simple solute, simple proportions. So let's look at a curve. And this is, I might be provided, the curve itself, the line, is representing the saturated but homogeneous solution. The area above the curve is considered saturated and heterogeneous. There'll be excess solute in solid form, so it will be heterogeneous. And the area below the curve is considered unsaturated. So it is fully dissolved, but more solute could be dissolved if we had it in there. And in general, at higher temperatures, more solute can dissolve. There's a couple of exceptions to that, but for the most part, things get more soluble as temperature increases. So if I asked, at what temperature can 40 grams of MX dissolve in 100 grams of water? Remember, how I use these curves is I'm going to look up the thing I know. I know 40 over 100, which would be here, 40. And then I follow over, okay, that's a little bit above the line, it must have moved. But if I follow over the fluidity to where it really hits, and then I go down, again, that's off, but you can see that where it would hit would be right here, which is a little bit shy of this 60 line. And I would go down and I would read what temperature it really is. It's around 60. I'd say it's actually more like 59. I probably should have edited that to be like 59 grams because it's a little bit shy of that. If I go back, you can kind of see that it's a little bit right here is where it's crossing. So that's before I get to the 60 line. So that might be, this looks like they go by fours, 44, 48, 52, 56. Yeah, so this might be 58. So I'd say a 58 would be a better answer. All right, let's try at 40 degrees Celsius. What is the maximum grams of solute can dissolve? Here I would start at 40. I would go up to the line, and then I see, okay, where does that ratio to? And if I look, again, if I take this before I put that up, you can see it's pretty much halfway between the 20 and the 30. Maybe a little shy of half. So it might be 24, it might be 25. I'll probably say it's 25. It's kind of right there in the middle. And being able to read a graph to its full precision, challenging, don't just like ballpark it. Really try to get very accurately where they are. You're going to get better values. Also, let's talk about, again, this weird part where normally we change we keep the bottom thing the same and we go up and down on the solubility. In this case, what we're going to be doing is we have a mixture, and I'm going to vary the temperature until it hits that point where it is saturated. It can't dissolve anymore, but still homogeneous. There's no solid, no excess solid. And so if I can once I find that point, that will be my solubility. So I could take a solid in water and there's too much solid. So it's not all dissolved. And I raise its temperature, so this is now, all of this part, it's saturated but heterogeneous. I still have solids on the bottom. I heat it up, heat it up, heat it up, heat it up, heat it up. When I hit this magic point where it all dissolves, that temperature is the solubility. If I continue heating it, now it will be unsaturated. There's more solid could be dissolved. Or I could start with a unsaturated solution at a high temperature. So now everything is dissolved and it just looks like a solution. And I cool it, cool it, cool it, cool it, cool it, cool it, cool it. I see the first crystals. As soon as I see the first crystals, I know I've hit saturation, and if I continue to cool it, now it's saturated, but I have extra solid there. It's heterogeneous in mixture. And in that case, if I had a particular point, let's say this looks like 24, 28, 32, at 32 degrees Celsius, if I know what the mixture ratio is in standard units, and I subtract off the solubility at that temperature, the difference here between 20 grams and 64, maybe 63 grams. So 63 grams is how much out of 100 is what I have in the mixture, but the solubility is only 20. 63 minus 20 is 43 grams. That 43 grams would be in solid form. So I can use these techniques. And again, that's in a theoretical 100 gram of water mixture. If I really didn't have 100 grams of water, once I got that answer, I would scale it back to what would that be? And I would scale everything back. What would be the true mass in the mixture? What would be the solubility for that ratio of water? And subtract those to get the amount that's solid. There is such a thing called supersaturation. Supersaturated, so we have unsaturated, it could dissolve more. We have saturated, it's exactly at the maximum point of how much it can dissolve. And you can get to this supersaturated point where more is dissolved than can be dissolved. And you're like, well, wait, I thought you just said you had the max. How can you have more than the maximum? Again, it's this very unstable condition, and it's kind of rare, and it's sort of cool. You should watch. I put some, YouTube link down there, but look for it. Like, the idea is that the slightest change, because it's so unstable, you shake it, you scratch it, you bump it, you stir it, and all of a sudden everything, like a whole bunch of, because all that extra beyond the maximum can't be dissolved, it really shouldn't have been dissolved, it all like falls down, it all precipitates and turns solid and falls down very quickly, and it looks pretty cool. But there'll be none of that in this lab. When we hit the point of saturation, we'll have saturated or unsaturated, but we could have saturated where there's too much there. It's not dissolved though. The extra, the too much, would be in solid form, so it would be heterogeneous. That's what we're gonna have. So we're gonna have three kinds of solutions: unsaturated but homogeneous, saturated and homogeneous, and saturated and heterogeneous, meaning there's extra solid in there. Okay, let's look at some problems that we see. This mixture ratios and scaling tends to confuse people. Remember, when I'm on the graph, I'm thinking that's my standardized world per 100 grams of water, and then in the lab, I have a different amount of water, and I'm gonna scale back and forth. So one task might be calculate the mix. So is this saturated homogeneous, saturated heterogeneous, or unsaturated at a certain temperature? So I could calculate the mixture ratio and compare it to the solubility. So you say I got 13 grams in 50 grams of water, and I would say, well, what would that be if it was 100 grams? I would look that up as a solubility on my chart, find the temperature, and that would be the temperature at which it could dissolve. If the mixture ratio is equal to the solubility, then I'm at saturation. I'm at saturated homogeneous. If the mixture ratio is greater than the solubility, then it's unsaturated. Then it's saturated and heterogeneous. If the mixture ratio is less than the solubility, it's unsaturated. So I have my solubility point from the graph. I have to compare it to a mixture ratio that's been scaled to 100 grams. And I compare those numbers. And depending on which one's bigger, I can determine it. Or I can scale the mixture ratio to be per one. That's what I just said. Okay, I could scale the solubility. I could look up the value on the solubility chart and say, well, let's scale that down, my solubility, to what the lab ratio is, and then compare the numbers. But the idea being, I'm going to compare what's in my mixture, what is the solubility that I get from the graph. But they have to either be they have to be in the same amount of water. So I have to scale it one way or another. So here's a couple examples. Describe solution if 70 grams of My in 40 grams of water at 25 degrees Celsius, if the solubility of My at 25 degrees Celsius is 72 grams per 100 grams. So I'm giving you the solubility rather than you having to look it up on a chart. So I'm going to scale one of them. In this case, I'm going to scale my mixture ratio. My mixture ratio is 70 per 140. But how many grams would that be if it was just 100 grams? So if I scale that, it turns out it's 50 grams of My per 100 grams of water. So that's my mixture ratio. Now I say, what is the solubility? It's 72. My mixture has less than the solubility, so it's going to be unsaturated. Or I could have asked you with a curve, will 70 grams of Mx in 140 grams of water at 25 degrees Celsius be saturated? Or I could ask you to describe it. So I would look here. I need to first, to use this chart is in per 100 grams. So I'm going to scale 70 per 140 to how many would it be per 100? And I get 50 grams per 100 grams because it's the same numbers we just did. So then I would find where is 60 on the chart, or 50 on the chart. Note that it's here. It's above the curve. That means that there is more than can be dissolved, which means this is going to be saturated but heterogeneous. So it is not, it is saturated, but it's saturated and heterogeneous. So that's true. And now if I asked you, well, how much would be solid? You could calculate it by subtracting. So in this case, if it was 50 grams, 18 grams would be dissolved. And then I could scale that 18 grams of, well, what would that be per 140 grams of water? And then I could subtract 70 minus that, how much would be dissolved, and the remaining amount would be the mass of the solid. All right, so in this lab, you're going to share data. You have to take 3 temperature points for each mixture. You're going to make a mixture and heat it up till it's fully unsaturated, cool it down till it hits that saturation point, record the temperature. Heat it back up, cool it down, record the temperature. Heat it back up, cool it down, record the temperature. So you're going to get 3 crystallization temperatures, which will be the temperature at which you've hit saturation, and you have your mixture ratio is now a solubility. And you're going to do that 3 times, and then you're going to change and make a new mixture. Really, you're just going to add more water, which changes the proportion, and you have a new mixture and you repeat it. So that's 5 mixtures, 3 points each, a lot of heating and cooling. If you do a good job, you can't do that and do both solutes. So I'm just going to assign one lab group, we'll do KCl, the other one will do KNO3. I've assigned randomly the ones near the windows are going to do KCl, and you're going to then swap data with the group next to you. And we'll keep track of which ones make sure I'll have you know which ones you did and which ones you got from the other lab partner. So if it's KCl, and there's almost the same difference between the two of them. You're going to start with 7.5 grams of KCl. You're going to, in a test tube, you're going to add 15 milliliters of water. That's going to be your good initial ratio. And you'll use a hot water bath that's been sitting, instead of on a flame, you're going to use a hot plate. Works the same. And you're going to heat it up till it's all dissolved. Note that in here we have this stirrer. This orange thing is like a stirrer that fits around the thermometer. We'll be using analog thermometers. They're a little bit better with temperature change. And you're going to be stirring it the whole time by lifting the stirrer rod up and down and making sure it's staying well mixed. And then once you have it all dissolved, you'll take it out of the hot water bath and cool it down. You have to continue stirring it gently so that it is staying stirred. And look for crystals. When you see the crystals, you measure the temperature and record it. Repeat the process. To make a new mixture, we're going to add more water. We're going to make it more dilute, which should lower the solubility, the crystallization temperature. So you'll add another 3 milliliters-ish with the burette, again, recording all your values, and then repeat the whole process. In general, your 7.5 kilograms of KCl should end up being mixed with first 15 milliliters, then 18, then 21, then 24, then 27. No, we're adding 3 milliliters each time. And again, it doesn't have to be exactly those numbers. You need to know how much you added each time so we can calculate those ratios. But those ratios will work very good in this lab. That's why we've chosen them. When you get down to the final two temperatures, final one, you'll probably need an ice water bath. If you have to go below 0, ice water can only get to 0 degrees Celsius. We have some negative Celsius crystallization temperatures. You may have to go to a ice salt bath. That's really more with KNO3. Okay, so the KNO3 part is very similar for the groups that have that. However, instead of starting with 7.5 grams, you're starting with 15 grams. You still add 15 milliliters for your first mixture. And then when you're doing each one, you're not going to add 3 milliliters, you're going to add 5 milliliters. And you have to do one more. So you'll go all the way up to 55 milliliters of water. If we're worried about time, we'll skip probably the 30. And you'll do 15, then 20, then 25, and then add 10 instead of 5 to 35 and 55. And when you get to those last 2 points, you're probably going to need an ice salt slurry to get cold enough temperatures for it to crystallize. So that's the lab in a nutshell. When we're done, you're going to make a solubility curve. We'll talk about this I'll make another video for analysis. But basically, first I have to take all my data and convert it to standard solubility. And then I have multiple temperatures. I have the individual 3 temperatures, and then I'm going to average them, and I'll have an average. So I kind of have like 4 points for each mixture. But I want to consider the average to be a separate curve from the individual temperatures. And then I want to do KCl and KNO3 on the same graph. So I'm going to have 4 different series. The individual temperature, the average temperature for KCl, the individual temperature for KNO3, and the average temperature for KNO3. And that's going to be a little tricky. We're going to do scatter XY with 4 series. The average temperatures, I want you to add a trend line. So that's going to be a little bit trickier. We'll talk about that on the next video.